you. So I put this up there because so we can just refresh our memories. So in this example, the moduli of H max to an affine Q variety X are the abstract filtrations become something rather concrete. It's just a filtration of the underlying, here, filtration of the underlying vector bundle along with an assignment of weights. And I've used the other presentation here where these W's, it's a Z-weighted filtration, but these W's are remembering where the filtration jumps. And the numerical invariant is given like this. And then there's an LX term, which is the Hilbert-Mumford. And basically, the theorem, I should mention, it's joined with Andres Fernandez Herrera, who's not in the room right now, but he's here, and with a lot of helpful input from Eduardo Gonzalez. But the theorem basically is that this mu determines the theta stratification. So mu satisfies this monotonicity and HN boundedness. And therefore, so the moduli of semi-stable gauge maps has a good moduli space. Is proper over the affine GIT quotient. So this I just mean spec of the ring of invariance on X, and mu determines a Harder-Simon stratification. There's more you can say, but this is roughly the theorem. So basically, there's two conditions. This is known. So this is the existence of this moduli space. These are just the moduli of solutions of the vortex equations. This is the algebra geometric thing, which I guess goes back to Schmidt for a general construction. So the existence of this moduli space was actually known, and what's sort of new here, I guess it's a different construction that does not use GIT, but then, there's Andres, he's here now. And then what's new is that you get this sort of Harder-Simon stratification of this moduli problem. So today I want to explain a little bit about why this is true, a little bit about the proof, and then also about the application. So I'm going to monotonicity. I'm going to actually mostly skip, unfortunately, for lack of time. But I did want to say one thing is that in the case of GIT, in the case of classical GIT, so some comments though, is that this is where the requirement of finding. So both of these steps require some ideas, basically, to prove it. But this monotonicity condition is basically in classical GIT. This this is why you need the bundle to be ample. So one of the mysteries when you're setting up, if you want to know if you have the right moduli problem or the right line bundle moduli problem, you know, you say, what is the right line bundle? And in GIT, there's an answer. It's the ones that are ample on X itself. In this case, these are the line bundles. Basically, what you can do is you can imitate classical GIT, and you can set this moduli problem up as an instance of an algebra geometric version of infinite dimensional GIT. And the important thing is that the line bundles that are used to define semistability in this case is ample on these generalized affine Grassmannians. So there's a picture that I doubt that I will have time, that maybe I can answer if someone has a question in the end or wants to understand what affine Grassmannians have to do with this picture. But there's of course, for vector bundles on a curve, there's a famous kind of like uniformization, or I mean, even more, it's even easier for a semi-simple group where you just remove a point and it's a quotient of the usual affine Grassmannian. The stack itself is a quotient in some sense of the usual affine Grassmannian by the group of maps from the affine curve into the group G. There's a picture like that for this moduli problem as well. There's a sort of in-projective in scheme quotiented by an ind group in some sense, and the important thing is that the line bundles that you chose are ample along those in-projective in schemes. So I don't want to get into that. I want to show you something else, which is like somehow less technical and also and equally at the heart of the matter. So I'm gonna. But I wanted to comment a little bit on what goes under the hood here. It's a different infinite dimensional GIT setup than happens in the symplectic world. I mean, in the symplectic world, for infinite dimensional GIT for these moduli problems, the space itself that you're quotienting tends to be very simple, like the space of connections is sort of contractible, and the gauge group has all the topology. And this is kind of the opposite, where the gauge group tends to be contractible, and the space you're quotienting, these affine Grassmannians, sort of carries all the topology of the moduli problem. But anyway, that's not just a bit of a time. What I really want to talk about and go into some detail, the only kind of detail I'm going to give you is, just because I think it's fun, is this HM boundedness. So the definition of HM boundedness, so that one of the inputs, one of the criteria that you have to check is that for a bounded subset, by bounded here, I mean, you know, this moduli problem, there's no finite type scheme that parameterizes all the objects in this moduli problem. So a subset of the stack is bounded if there's some finite type scheme that parameterizes all the points in that subset. So for a bounded subset, U inside of so this is stack X. For a bounded subset U inside of here, there's another bounded subset. U prime such that for any point in U and filtration F of P, there exists another filtration, F prime, with the filtration of the same point, and mu of F prime is greater than or equal to mu of F, and ger of F prime lies in U prime. This is the condition that you have to check. So basically what it's saying is that if I'm trying to remember, we have this numerical invariant, these numbers here, And I'm trying to find, given a point in the moduli problem, I'm trying to find an f that achieves a supremum for the value of this numerical variant. And so you can imagine how this condition would be helpful. Basically, it says, if I want to find a f that achieves a supremum, it suffices to consider only filtrations whose associated graded point lies in this bounded subset U prime. That's what this is saying. So for the purpose of optimizing, in words, for the purpose of optimizing mu, of maximizing mu, it suffices to consider filtrations whose graded point lies in U prime. This actually implies the existence of a maximizer. The monotonicity implies the uniqueness, but again, I'm not really getting into that. Okay, so what I want to do is first describe this just describe it for Bun. So I promise that this is a different way of thinking about the Harder-Simon filtration of a vector bundle. And so I would like to, if there's one thing I can deliver, I would like to deliver on that promise and explain a different way of thinking about a different proof of the existence of Harder-Simon filtrations for vector bundles. So the idea is if you fix, so I'm going to verify this condition so fix an unweighted filtration. So even though changing the weights algebra geometrically actually puts you on different connected components of the stack of filtered vector bundles, but in some sense it makes sense to say fix an unweighted filtration. So I'm going to fix my E, and I'm going to fix an unweighted filtration, and then basically there's a cone, sigma E. And this is the, it lives inside of, well, and this lives inside of like a copy of r to the p plus 1. And so basically you can think about these, so the integer points or in here, actually parameterize what I was calling z-weighted filtration. The integer point that assigns the weights. But there are all these other points, and actually this function is scale invariant anyway. So you can think of rational points. So this function is now, I've rewritten it as just a function of finitely many weights where the jumps are happening. So you look at this function, it's a sort of continuous function, and it's scale invariant. So you might as well just consider it. I mean, it makes sense to think about this function for any real weights, even though that doesn't have as easy an algebra geometric interpretation. And so I should say, actually, the interior, so if these are really where the thing is jumping, there's a strict inequality there. So so the interior of this cone parameterizes weighted filtrations. Yeah, and the boundary, so if I think what is the boundary of this cone, well, that's where if I take the locus where wi is equal to wi plus 1, inside of sigma e. So again, these weights, you're thinking about this as you have a z-weighted filtration and the weights are recording where the jumps happen. So if two of the weights collide, basically that jump just doesn't happen. So this actually, as a cone, you can identify this with a cone for a different filtration, namely where, where E prime is the filtration you obtain by deleting, I guess, the I plus first. And the reason why this is a reasonable thing to do is because if you look at this function here, it's not hard to show that under this identification, the function it preserves this function basically. So this function is defined on this cone, the L1 divided by Lx. But if you go to the boundary, you think of this as the weights on this other smaller filtration, it's compatible with the function that you define there. So then it makes sense to glue, because the function is really, is sort of compatible with these identifications of the boundary, so you can glue and you get this thing, which is this is an instance of a more of a sort of general object, which is the degeneration fan, the geometric realization of the generation of what's called the degeneration fan in this theory, but this is what it is in this example, and it's just a union over all unweighted filtrations, like this. So it's a huge thing, but the point is that it's been constructed in such a way that mu gives a well-defined function to R. So I have all these different cones, these abstract cones. I glue them together via these identifications, and I still have actually a function that's continuous on this glued topological space. So in some sense, now this problem that I'm asking for is there, so take an unstable bundle. Think about an unstable bundle. So an unstable bundle means an E where there's some point on the space where the value of this function is positive. That's what unstable means, is that there's some filtration with weights that makes the numerical invariant positive. So if I'm in that situation where there's some point where this is positive, why is there a maximum achieved? And it's not really very obvious why there's a maximum achieved, because this is like I said, there are really sort of hugely, infinitely many actual filtrations of the vector bundle. So this is kind of it's a finite dimensional but very infinite sort of kind of simplicial complex sort of thing. You might think of it as the spherical building of the gauge group. If you're like into this, if that has meaning to you, that might be a helpful way to think about it. So the goal is to maximize mu. And now this is where this whole thing becomes a kind of it becomes optimization problem. So it's very easy to show that on any given cone there is a unique rational maximizer for this function. I mean, basically the function is scale invariant and continuous, and if you take the cone and you quotient by the scaling action, you get a simplex, you get a compact space. And so a continuous function on a compact space has a maximizer. But that's even more abstract. You can literally just write the maximizer down in this case. So the hard part is why, even though there are infinitely many cones, on every cone there's a maximum. So the question is, why does it suffice to consider only finitely many cones in some sense? So I want to argue that I can reduce this optimization problem on infinitely many cones to just thinking about it on finitely many cones. And that has to have a solution for the reason that I just said. Right? And the key idea is that so first I want to So the key idea is if the unconstrained max, there's a constraint. So I can consider this function happens to be a function on this larger vector space, even though this larger vector space doesn't really have an interpretation. It's only this cone that I can interpret as filtrations. This vector space is just something else. It's just formal. But I can still consider the unconstrained. If the unconstrained max W star lies outside of the interior of this cone, that implies that the constrained max will lie on the boundary. And this is because this is like a convex optimization problem, so this is kind of a general property of this convex optimization problem.
Sorry, what's the constraint that W0 is less equal to W?
Yeah, the constraint is that it should lie, I'm looking for a maximizer on this cone.
Maximizer of that function.
Of that function, yeah. It's a very concrete thing. I'm looking for a maximizer function on this cone. And if you can take the unconstrained max, and if it lies outside the cone, that tells you that the constrained max is going to lie on the boundary. And because of this interpretation, the boundary of this cone really is just a cone for a different filtration. So I can actually just ignore the filtration.
But just a question, the unconstrained max exists necessarily?
Yeah, I'm going to make a comment about that. I can write it down. I can just tell you what it is, yeah. The constrained max lies on the boundary and implies that you can ignore this filtration. So you want to sort of argue that with the exception of sort of finitely many cones that can appear, I can ignore most filtrations. That's like how this argument works, and this is the idea. To look at the unconstrained max, and if it lies outside the constrained max, has to be on the boundary. In other words, it's captured that whatever point it is captured by a different filtration anyway. So you might as well not even consider this filtration. And I want to say this is the lemma that I learned in my summer as a hedge fund manager. But this is the portfolio optimization. So actually maximizing, I should say, so on Bun there's no LX. This thing doesn't really appear on Bun G, it's just L Bun. But maximizing mu equals L Bun divided by square root of this quadratic form B is equivalent to maximizing L Bun minus 1/2 B. So this is now like a nicer thing. This actually is a linear form minus positive definite quadratic form, and so there actually is this has a well-defined maximum only up to scale. It's a normalized linear form, has a maximum only up to scale. This has an honest, well-defined, unique maximum. That's actually, but the point is that whenever that maximum occurs, actually is also a maximum here. And actually, this thing, if you choose a basis, if L Bun is equal to L transpose times the weight vector, and B is equal to the weight vector transpose times a positive definite matrix times B, then the max W star is equal to B inverse times L. So you can just Lagrange multiplier, maximize this, and you just get the answer. So in this example, in fact, it's very easy. So for here, in fact, what you get is that W star is the following. So it should be a vector of weights, and what it ends up being is D0 over R0 minus D over R, comma, dP over RP minus D over R. Just using this formula applying it with this example, where DI is the degree. I should have said maybe D is the degree of E. Capital D is the degree of the bundle E. That's fixed, and R is the rank of E. All right, so there's the unconstrained maximizer. You can just do it. And so what does it mean for this maximizer to lie in the cone? Well, it's precisely the condition this lies. So this lives in our P plus 1 E. And this lies in the interior of sigma E if and only if, so this, this should be a strictly increasing sequence. So D0 over R0 is less than dP over RP. And these are the slopes of the associated graded pieces. So it's saying the slopes of the associated graded pieces should be strictly increasing in a sense, which is just the same thing as saying that the filtration is convex. Yeah. So this is the observation. It's an optimization theoretic argument why it suffices in this example to just consider convex filtrations. And then there's a key input from AG, from algebraic geometry. And this is the boundedness thing that I was talking about. The input is that the set of unweighted convex filtrations of E so if I fix my bundle, or more generally, if I let the bundle vary in a bounded family, then the set of unweighted convex filtrations is bounded. And basically a consequence of that is that only if I consider now, so in other words, by this key idea here, I can ignore many of these cones. I can just ignore for the purpose of optimization. Because I can always find a convex filtration where the numerical invariance is bigger. So I would just consider convex filtrations. That gets me to a bounded family of unweighted filtrations. But in particular, there still are infinitely many filtrations. But in terms of the cone that I get, in terms of the cone and the value of the numerical invariant only depends on the ranks and degrees of those filtrations. So basically, there are finitely many shapes for these filtrations. So technically, there's redundancy. I still have infinite many cones. Exactly what subbundle of rank 5 and degree 2 or whatever. There are many choices, but the point is that if I look at the ranks and degrees of the bundles, only finitely many things will actually appear because the family of such filtrations is bounded.
And I understand this is really the only serious input from algebraic geometry.
Yes.
The rest is just
optimization.
Convex optimization.
Yeah, the rest is convex optimization. Yeah.
I've been teaching that course. I know that.
Exactly. Yeah. So I taught a course on this to learn it when I knew that when I could sense that this problem was going to go in this direction. So the rest is just convex optimization. So anyway, that's the argument for why there's a maximizer. Now, are there any questions?
Maybe I'll just make a historical comment. So this thing on the bottom line, right? Like just in the case of finite dimensional GIT quotients, it's like thinking of the Lie algebra as the disjoint union of the different conjugations of the maximal torus.
Yes. Yeah. It's a horrible thing to do topologically.
No, but there's even a name for it. I think it's called like the Boozman. Isn't it called the Boozman topology or something? There's this in the Donaldson-Kronheimer chapter on finite dimensional GIT quotients. They actually made the claim that the asymptotic slope was continuous as a function on the unit sphere in the Lie algebra.
I see, but that's
And
not
that's
right.
false.
No. Yeah.
But if you look at the Boozman topology, then it's true. But then the optimization problem becomes a little bit more complicated. I'm not
exactly
100% sure about the name of the topology.
I mean, I don't know who calls it what, but it's called the spherical building. Is another way to call it. Yeah, it's called the spherical building of the group. It's a giant simplicial complex. Yeah. Anyway, so that's so this is like maybe you were working for the comment before, but you can think this space here you can think of as the spherical building for the gauge group. It has that weird topology. for the gauge group. So now I want to say what happens. So the question is, what happens? What's the issue now for mg of x? So for simplicity, I just erased it, but we have L bun, and we have B, and there's Lx when I go to x mod g. In other words, I can incorporate. There's a way to incorporate a GIT parameter on x itself, into the vortex equations as well. That's the moment map. But actually, I'm just gonna, for this purpose, my GIT parameter will be just the trivial line bundle that works on an affine target. So basically, there's no. So I'm still going to consider, for simplicity, just L bun divided by the square root of B, which is fine. I mean, you can think of this as using the trivial GIT parameter. But what's the issue? So here, the point is that not all weights are compatible with the additional data. So remember, in this moduli problem, it's a vector bundle. Oh, I'm still working with GLN here, just because it's a vector bundle along with a section of some associated bundle. And the issue that we're going to run into is that actually, if I consider I have some cone, sigma e, and this parameterizes all weights of the underlying bundle, but not all of the weights are remember we had the condition in the example of algebras that EW.EV should be contained in EV plus W. This is in the z-weighted picture. And so not all choices of weights are compatible with these kinds of restrictions. And if you actually do it out, you can show this in general. What there is actually a subcone inside of here, which I'll call sigma x. So when I impose the condition that it should be compatible with the section in x, I get a smaller cone. Which doesn't seem so bad, except that, so before our argument was that the optimizer, the unconstrained optimum might lie out here. And so the constrained optimum had to lie on the boundary of this cone. And that's still true here, but the problem is that the boundary of this cone it doesn't have an interpretation the same way as the boundary of this cone does. The boundary of this cone we can interpret as a smaller filtration. So we argue we can just ignore this filtration entirely because the boundary of the cone is already captured by another filtration. But the boundary of this cone could lie in the interior of this cone, so it still might be like a length n filtration. I can't just discard it just because I know. So just because I know that W star lies outside of here, I can't discard this filtration, which is good because it turns out that the filtrations don't have to be convex in this example. In the final answer here that we're going to find, the filtrations don't have to be convex. So I can't just throw away all things where it lies outside that cone, So I'm going to explain to you. So yeah, this seems actually pretty hopeless. It seemed pretty hopeless for a while. Actually, I gave a talk on this a few years while this was developing. I gave some talks on it a few years ago. Where I didn't know how to do this, I could only do it when x was compact, and then you change the moduli problem to allow bubbling of the curve. And so there was like a more complicated moduli problem to write down where x was compact, and then we didn't have this issue, and I was stuck on this for a little while. But then, as we were finishing it up, I realized that there's a trick. So the issue here, just to write it down, is that you can't necessarily discard E. Because it might be on the boundary of the larger cone, but still correspond to the same filtration. On the boundary of the smaller cone. So I'm just going to sort of outline what we do. So first of all, the first thing to do is to compactify So X is affine. I'm going to compactify. Actually, technically, it's a compactification relative to X mod G. But let's just imagine, in other words, spec of the ring of invariance. But for simplicity, let's just imagine that spec of the ring of invariance is just the ground field. And you can compactify such that X is semi-stable for some, is the semi-stable locus for some L in pic G of the compactification. So you basically, this is the GIT semi-stable locus. And what this compactification allows you to do, so this forgetful map here, the forgetful map from MG to Bun is affine. So it has affine fibers. But choosing a compactification of X allows you to give a relative compactification, which has the same name, but the definition is a little bit more complicated. It involves, instead of just sections of an associated bundle, what you want is a Kontsevich stable map to the total to the associated bundle whose projection down to C has degree 1. So effectively, this is a different moduli problem that's sort of Gromov-Witten-ish. It's what Woodward and Gonzalez have studied with the Gromov-Witten theory, and basically it allows bubbling in the fiber direction. So it allows genus 0 bubbles to form in the fiber of your section. And the point is that this is a relative compactification. Yeah. And actually the point here is that all filtrations in Bun lift uniquely to this mg of x bar. So because it's a little lemma that because this is a relative, this morphism here is compact, a filtration, a map from A1 mod GM to Bun lifts, lifts uniquely to this thing upstairs because it's compact, that morphism compact. So now, on this moduli, if I'm asking to find Hardy-Narasimhan filtrations on this moduli problem, it's now all of a sudden achievable. Because it goes, now the same picture works where the cone returns to being the entire cone. And I can use the same argument. So if I don't modify the numerical invariant at all, I get Hardy-Narasimhan filtrations on this compact thing, which is it's just the unique lift. Like I said, you take the Hardy-Narasimhan filtration and you can find a section with this bubbling phenomenon that is compatible with the Hardy-Narasimhan filtration. So that just is automatic. But that's not really the thing we're looking for, because the sort of associated graded point can have bubbles. And so it won't necessarily be a filtration in the original moduli problem. And so what you do is you deform the numerical invariant. So using this ample line bundle that picks out this as the semi-stable locus, I deform mu is now L bun plus Lx bar divided by square root of b. And I put a delta here. So when delta is 0, it's just the old numerical invariant, and the same exact argument shows that there's a maximizer. This is just the filtration, it's just the Hardy-Narasimhan filtration. And now you want to apply the same argument, so you have this cone here, and for most of these cones, W star, so W0 star, when delta is 0, lies somewhere, and then what you want to do is you want to sort of bound how far the unconstrained maximizer can move. So you want to argue So even though that you don't necessarily restrict yourself to convex filtrations anymore, but you can argue that for most filtrations, the unconstrained optimizer, for filtrations that are sufficiently non-convex, the optimizer doesn't enter the cone. And so the same argument kind of works, and so you're no longer restricting to convex filtrations, but you can restrict to filtrations that have bounded degree of non-convexity. And then the point is that as delta goes to infinity, you can show that eventually, so the maximum exists for all delta, but eventually the max, wherever it lies, so it's going to exist on some sigma e, but must be in this smaller cone sigma xe. So this additional term that you're adding effectively penalizes being outside of the cone sigma x. This delta, this Lx here on every Lx bar is going to look like the minimum of 0 and then a bunch of linear forms. So in any given cone, it's going to kind of have this functional form. It's a minimum of 0 and then a bunch of linear forms where that cut out exactly the cone sigma x inside of sigma e. And so the idea is for delta large enough, you're sufficiently penalizing being outside the cone sigma x that the optimizer, if it happens to lie in this cone here, has to lie in this cone here. Anyway, that's the argument. So I want to take a few minutes to talk about the applications of this stuff. And I did promise that. And usually I begin with the applications, but I figure for this audience, this is essentially studying sort of the kind of analog of Taylor-Ricci flow or whatever. I mean, what do they call in this case? Taylor-Einstein flow. I mean, sorry, I'm not a gauge theorist, but I'm doing my best. But like, this is there's this functional, this deform-Yang-Mills functional for the vortex equation, deformed by the mode map, and you're trying to study the natural kind of flow to minimize that functional. And what this is saying is, in algebra geometric terms, this is saying that flow actually converges in the same way it does in the Atiyah-Bott picture for just pure gauge theory on a Riemann surface. And so I figured for this crowd, maybe having this result and the convergence of this flow is kind of interesting enough. But I did want to talk about some applications. So basically, the main application of having a theta stratification. So theta stratifications let you compare the geometry of mg of x with mg of x semi-stable. So this, for instance, if you choose your linearization, there's a choice of linearization on x, and if you choose it to be large enough, you get into a chamber where the semi-stable locus are just the stable quasi-maps that are studied quite a bit in enumerative geometry and have come up a few times here. So the stability condition, like as I mentioned, the stability conditions on this thing have been studied. That's the vortex equation, basically. And so for large enough, if you take any linearization x and scale it up, you get to something that's very familiar. It's just this quasi-maps thing. And that's comparable. So this is comparable to Gromov-Witten moduli spaces via techniques developed by Woodward and Gonzalez. So the key application here is to say something very nice about the geometry of these moduli spaces for the large, actually in any chamber, for any choice of linearization, but the ones that are interesting for numerator geometry are when the linearization is large. And the kind of thing I want to do is I want to compute index formulas. So, I mean, classically in the Atiyah-Bott picture, if this was just Bun-G, the original stratification is also of this flavor, right? This is the mantra. A theta stratification allows you to compare the geometry of the whole stack with the geometry of the semi-stable locus. And so for the stack of bundles, Atiyah-Bott uses famously to compute the Betti polynomials of these moduli, of the moduli of semi-stable bundles, using some nicer topology that was available to understand the stack of all bundles. So that was like the original application. Basically, it was original theta stratification, the original application of this theory. But for me, I want to compare. I can compare. Basically, I want to compare the R gamma of mg of x so this is the line bundle that you use to define stability. So this is like a theta divisor. Tensor with an Atiyah-Bott complex. Let me call this, I'll call that F. So basically, there are sort of tautological complexes that you can write down on this moduli stack that come from the usual Atiyah-Bott picture, where you take something, you take a representation of the group, and you look at the associated vector bundle on C times M, and then you push forward along the curve. You integrate along the curve, tensor maybe with some K-theory class on the curve. So this is a sort of K-theoretic version of the Atiyah-Bott classes in K-theory. And L, and I want to understand this index, but more specifically, I want to compare it with the index So I have this restriction map. The restriction. So I have a complex which is the cohomology of one of these special line bundles, the one that I use to define semistability on this stack, tensor some interesting Atiyah-Bott class, and I want to compare them via this restriction map. And I won't get into the details of this. I mean, I think they're interesting, and so I mean, well, they're interesting to me, and there's a whole other story there. But I just wanted to kind of at least explain for you why I've been talking to you for 3 days, like what I've been building towards. So the theorem, I think I might be quite a little bit out of time. Oh, I'm exactly out of time. Can I just take like 2 minutes to state that?
No, it's okay.
Oh, okay. All right. So the theorem is the following. So the theorem is, first of all, R gamma over the stack. If I take the cohomology over the stack of all gauged maps of these classes here, and R gamma mg of x. So here, and at this point, actually, I've switched where for this theorem, x is a linear representation. There are ways to access complete intersections in linear representations as well, but just for cleanliness, let me just state it for a linear representation. So this is a sort of a gauge linear sigma model. Both of these cohomologies, so these complexes have finite dimensional, have bounded cohomology. That's coherent over the affine GIT quotient. And I should say that x is a linear representation, so you have a scaling there's an additional scaling action that commutes with x, and so even when this thing is non-compact, the scaling action equips both of these cohomology groups with an additional grading. But anyway, so the theorem is that the restriction map that I've drawn here from the cohomology on the stack to the cohomology in the semi-stable locus is an isomorphism. For M sufficiently large. So if you fix an Tiamat class, and I take what they call a large enough level, this is the level line bundle. If I take a large enough level in my Tiamat class, then the cohomology on the stack is the same as the cohomology on the semi-stable locus. And then the third thing is that the graded Euler characteristic of this cohomology is computed exactly. Using the Telemann-Woodward index formulas. And so the idea is that this stack here admits a forgetful morphism to bun G. With its fibers are affine. And so if you want to do an integral on this, so basically what this is getting at, if I compute the index, so okay, let me make some comments here. I'm not going to write anymore. My chalk time is over. But it's a little bit surprising that something like this would be true. This is an unbounded stack. It's some kind of enormous thing. And so you write down some coherent sheet for some vector bundle. Why on earth should the cohomology groups be bounded or finite dimensional? So that's like a kind of remarkable consequence of having this theta stratification and applying some of the machinery of derived theta stratifications. This consequence. And then, but the really nice thing in this example is that if I want to compute this, so I can think of this as the Euler characteristic is like computing an index. It's like a k-theoretic gauge-Grove-Witten invariant. So actually, literally the index, the Euler characteristic of this is literally a k-theoretic gauge-Grove-Witten invariant. It's an index of some tautological vector bundle over a moduli space of quasi-maps. And so the cool thing, though, is that here, this thing fibers nicely over bun G. And when you push forward and do the k-theoretic integral on bun, so you first push forward to bun G, and you reduce this index calculation on the whole stack to an index calculation on bun G, where there's lots of control over the index. And it turns out you can literally just write down an explicit formula for the Euler characteristic of those complexes. And so using this theorem too, you get explicit formulas for the gauge-Grove-Witten invariants. Okay, so that's like the main application that's kind of in this paper, but and so I just wanted to include that so you had some sense of what this is all driving towards. But thanks, I'll stop there.